Welcome to Hammond Power Solutions Power Quality Overview Intermediate Training Module. The measurement of electrical power can be defined as the rate per unit time at which electrical energy is transferred by an electric circuit. A common measurement would be the kilowatt hour. Power quality can be defined as a quality of this electrical energy that is being transferred by an electric circuit to perform work. As per IEEE, power quality is also defined as the change in the power affecting measurements such as voltage, current, or frequency that interferes with the normal operation of electrical equipment. IEEE defines several main power quality issues including blackouts, voltage sags, voltage spikes, harmonic distortion and voltage notching, voltage unbalance, and power factor. There is also the reflective wave issue, which affects the VFD output to the motor. While reflective wave isn't typically associated with IEEE power quality definitions, for the sake of this discussion, it will be included. Other than blackouts, HPS offers a wide range of solutions for these power quality issues. Please take a few seconds to review this chart to familiarize yourself with some of the common products, including line and load reactors, drive isolation transformers, active harmonic filters, DV/DT filters, harmonic mitigating transformers, and options such as latent arresters, snubber circuits, and surge protective devices. IEEE 519 establishes levels of voltage and current harmonic distortion acceptable to the distribution system. These levels are based on the input transformer's characteristics and the loads on a facility. The facility's input transformer is where the utility transfers power. This is called the point of common coupling, and it is where these voltage and current harmonic distortion levels are typically measured. The current and voltage harmonic limits are set by IEEE and are followed by many utilities and are clearly outlined in the following IEEE tables on this page. While we could spend several more pages discussing this standard, let's highlight the main talking point of this presentation is limiting total harmonic distortion of the current to below 8% on systems lower than 1,000 volts. Earlier IEEE 519 standards limited the total harmonic distortion of the current to below 5% and are still commonly used. Note the current distortion percentages are based off the load's total harmonic current divided by the system's maximum continuous current capacity, not the actual load. The quality of electrical power is important. Almost everything is run by electrical power. Power quality is a major concern for both utilities and their customers. Utilities are concerned because poor power quality can cause customer dissatisfaction and equipment and revenue losses. Customers are concerned because system disturbances caused by poor power quality can cause thousands and millions of dollars in production and equipment losses. These graphs show the very nature of power quality problems. There is no single solution to a power quality issue. Systems may experience one or more of these issues. As a result, a successful diagnosis of the problems which are occurring or are expected will result in the best and most economical solution. HPS has a wide variety of solutions which can be applied. Harmonic distortion is a distorted voltage or current sine wave. There are many causes for harmonics that all revolve around nonlinear loads. Nonlinear loads convert AC power to DC power and include variable frequency drives, computers, UPSs, and lighting. This distortion is shown in the graph. The utility provides the perfect blue sine wave. The system's nonlinear loads add the smaller high-frequency sine waves, which proceed to distort the system's sine wave to the orange line. This distortion causes overheating of cables and equipment loss of efficiency in electrical machines, electromagnetic interference with communication systems, and nuisance tripping of thermal devices, to name a few of the most common issues. The reflective wave phenomenon occurs when long cable lengths between the VFD and motor are present. This creates large voltage spikes in the cable or motor windings. This is caused by both the pulse width modulated nature of the VFD's output, long cable distances, and differences in impedance between the cable and the motor. This results in voltage spikes of 2 or 4 times the VFD's DC bus voltage. The DC bus voltage is the square root of 2 times the system voltage. These high voltages can cause motor and cable failures if not mitigated. Notching occurs whenever AC power is converted to DC by a rectifier and using a nonlinear device such as an SCR. The process of commutation occurs, which results in a notch in the waveform. An SCR, or more commonly today IGBT switching, in nonlinear loads such as VFDs is very common. These notches can cause signal interference or damage with logic and communication circuits. These notches can also cause additional equipment losses. Voltage spikes are very fast variations of the voltage value for durations from several microseconds to a few milliseconds. Most spikes are a fraction of 1 cycle, but sometimes can be longer. Spikes are commonly caused by lightning, switching of power lines or power factor correction capacitors, disconnection of heavy loads, and harmonic resonance. These spikes can cause many issues, including damage to electronic components, degradation of insulation materials, and arcing or coronal discharge. In conclusion, the impact of poor power quality can cause many issues, including reduced operational efficiency, unplanned outages and downtime, premature equipment failure, and increased running costs. There are many solutions available to mitigate power quality issues. The importance of maintaining good power quality includes limiting downtime, predictable process outputs, improved energy efficiency, reduced operating costs and energy waste, and improved reliability. Please contact HPS at any time to discuss power quality solutions.